First of all, I'd like to thank for inviting me to give this lecture. I'm also part of the project, but we thought let's start with ourselves, and in doing these UDAN lectures, which are really a great opportunity. And in that context, I'd like to say hello to everybody. Good morning in Germany and good afternoon in India. So my talk is about how debris damages dams and why we need more geomorphology in hydropower safety assessment. So the key points I'm going to make is that, well, first of all, Himalayan hydropower is on a steep rise with severe impacts on the environment. I will show that recent hydropower damages highlight the vulnerability of Himalayan hydropower to geomorphological extreme events. This warrants that we should look more deeply into geomorphological questions when trying to answer questions about Himalayan hydropower safety. I will show that terrain analysis provides the tools and measures to characterize sensitive landscapes and to predict damages. So I will show that in a case study. And then I will show that accounting for geomorphological extreme events reveals limits to hydropower expansion. At the end of this talk, I'd like also to give a few research recommendations and avenues that we could strive within this project. Okay, so you all know, I guess, that hydropower is on a steep rise. Currently, hydropower supplies about 16% of the world's total electricity, and it's one of the major renewable sources of electricity. This source of energy is particularly important in these emerging nations like India and China, because their increasing energy consumption is partly covered by hydropower expansion. There is also, this development has actually led then to a renaissance of large hydropower projects. And this development was fueled by a lot of political decisions also at the global level, such as the Kyoto Protocol's clean development mechanisms. So a scheme that enables developed countries to offset carbon emissions by supporting CO2 neutral or environmentally friendly projects in other countries, as well as another one that fueled this development is the World Bank's development agenda. So with 450 large and 600 small hydropower projects that apply only for these clean development mechanisms in the Hindu Kush Himalayas, that region is expected to have by far the largest growth rates in hydropower in coming years. In Nepal, this development is particularly strong. So we can see here that about 100% of the domestic energy generation is done with hydropower. And we can expect that there will be a doubling of energy demand until 2025 compared to the level at 2018. And that basically calls for a need for new hydropower capacity. Based on recent data published by Bhattarai and Conway, we can see how this development will look like. So you see a map of Nepal on the lower left panel, which shows those projects that are currently under operation, which are those blue dots, those that are under construction, and those which are planned. And you see that there will be a significant increase in hydropower in Nepal as well. And some other regions already have experienced that development. Others are still about to experience it in the future. So there are a lot of advantages of hydropower. And it's good that we use it. It's a clean, renewable energy. It's decentralized, it's domestic, and it's a flexible power source. It can potentially create new sources of income in rural areas, and well, reservoirs offer a variety of good things, like fishing, irrigation, and flood control. Particularly for the poorer countries such as Nepal and Bhutan, hydropower also offers new ways of, or new opportunities of revenue, because they probably are able to generate more energy than they consume, so they can export it. In general, these projects have long lifetimes, about 80 years or longer. And well, as this map here on the right-hand side shows, it's published by Ghana in Nature Energy. And if you look at that bubble that represents the Ganges Basin, the one with the number 9, well, you see that in particular in the Ganges Basin and the Himalayas, there's a large remaining potential. So there's still a large untapped potential, and yeah, a lot of ways to increase hydropower production. On the other hand, there are also a lot of negative sides of this development. And let's say at the large spatial scale, water increasingly appears as a very critical issue in South Asian geopolitics. Also at a large scale, it's pretty unclear how climate change will actually affect Himalayan glaciers and as such water resources in the future. At the more regional and local scale, well, hydropower installment and the generation or the building of dams can create conflicts due to mass resettlements. That is something that we particularly observe in China. And then, well, dams along rivers actually lead to habitat fragmentation, which hinders the migration of aquatic species and potentially endangers fish diversity. In addition to habitat fragmentation, dams may also may cause more, well, or may create some impact on, let's say, water and sediment transport. And so even that occurs in particular, this occurs with so-called run-of-the-river hydropower schemes, which are actually thought to be more environmentally friendly because they don't dam as much water, so they don't have a big reservoir, but just directly divert the water from the river network. However, and that's just to show some recent studies that we are doing here in Potsdam, that's the master thesis of Arvid Schultz. So he is, for example, looking at the Sonkoshi run-of-the-river hydropower scheme, where he tries to take remote sensing data, so for example Sentinel, to survey in how far stretches of river fall dry due to water diversion. So in that map here, well, you see that river, that's the Sonkoshi River, which flows here from the right upper part to the lower left part. So here, well, that's the corresponding satellite imagery. And well, that's where actually large landslides happen. But downstream of that landslide, there's this diversion dam. From here, the water is diverted along the slope and then into some head-raised tunnels, where it's then inserted back into the river. So what that leads to is that in particular during the dry season, a lot of water is diverted and that stretch here falls more or less dry. And that can be actually shown using remote sensing data. So here you see the NDWI, Normalized Differentiated Water Index, which shows, of course, a high variability along that river stretch, but it particularly shows how a water signal basically vanishes in the dry winter month. So from, let's say, November, December, January to April. It's just monsoon month, then basically where river flow within that stretch is normal, and that's an issue that is not really regulated. It is regulated, but it's probably often not controlled in a way that this is water diversion is done in a sustainable way. Okay, but that's not exactly what I want to talk about today. What I want to talk about is more about hydropower damages and the extreme natural events that cause hydropower damages. So you all know Himalayas are a region of extreme events. It is a seismically active region, so earthquakes are common. And of course, these have effects on any hydropower infrastructure. Some direct effects like settling of the dam or cracks that may evolve. There are floods. We have a very flashy hydrological environment, and these create some risks for hydropower infrastructure. Dave Padley showed that a lot of landslides are actually associated with dams and reservoirs, so that's a kind of a problem, as well as glacial lake outburst floods, which, well, can create very rapid and high magnitude floods, which may cause damage downstream. So in a study also done here at our university by Marie Ryan, we actually looked at, well, what were the main or when did damages to hydropower infrastructure occur? So we searched a lot of gray literature, and well, what turned out is that, well, hydropower again and again had to or experienced a lot of losses, but that these losses particularly occurred during two natural extreme events that you are likely familiar with. The first one is the Indian floods in 2013. Here, more than 25 hydropower projects were severely damaged. And, well, the Roorkee earthquake with a 7.8 magnitude in 2015. Well, that event also led to a temporary loss of more than 30% of Nepal's hydropower capacity. So the study revealed that these events highlight the vulnerability of hydropower infrastructure to natural extreme events in the Himalayas. And they also, it also showed that, well, there is the potential that events such as these, that they actually undermine any strategies towards a sustainable development and use of hydropower. So the question is actually then, why were the damages to hydropower facilities so high? Hydropower facilities are actually designed for floods and earthquakes with return times exceeding more than 1,000 years. Did event magnitude exceed these statistical 1 in 1,000 years events? Well, Uttarakhand was one of the states that experienced most of the damage. And what I've just been trying here is to see, well, without good estimates of rainfall and runoff, because that's usually not available, but based on a study of Chopra et al., who published a couple of data, what I compared is, well, on the x-axis, the maximum 3-day rainfall during these Indian floods from 14th to 18th June, and the maximum 3-day recorded historical. For some of those, we even have some estimated 100-year return period. And we can see that, in fact, in many cases, the Indian floods were less than what was observed historically. So most of the stations that were published in their study basically had a higher amount of rainfalls experienced before. Of course, this is highly simplified because the 2013 floods were also characterized by additional effects like accumulated effects of event extent and other factors, e.g. that we had a lot of rain on snow, and that aggravated the situation. But overall, one has to say that the synoptic weather patterns that actually lead to these massive humid spells are actually also known. So it's something that must not have come totally unexpected. What about the Roorkee earthquake? Well, based on instrumental and paleo-earthquake records, estimated return periods for the Himalayan range for a size of, the Roorkee earthquake is about 80 to 90 years. So that's not very high in this context. So even for when accounting for the lower regional probability, return times would be lower than 1,000 years. So even if it was, then let's say a 7.8 magnitude earthquake is again not particularly high in the Himalayan context, where actually more than magnitude 8.5 magnitudes have been observed, and actually even 9.0 earthquakes could occur, at least following the study by Stevens and our work. So why were the damages so high? Well, when we look at imagery and reports from these events, we see that one of the main factors for damages was actually due to excess sediments, landslides, rock falls, and so forth. So this is an example from Vishnuprayak, which is a hydropower station in Uttarakhand, before, during, and after the Indian floods. And you see the massive scale of sediment delivery and sediment accumulation at that site. So this yellow arrow points at one of the houses here, which is more or less completely submerged in sediments after the floods. The earthquake, also showed high damages, and what we can see here again is Upper Trishuli, or the site of the Upper Trishuli hydropower project. 2009, the hydropower project didn't exist yet at that time. 2014, the hydropower project was apparently more or less ready to go. In 2015, shortly after the earthquake, we can see the massive scale of disruption on hill slopes adjacent to the hydropower project and the Trishuli River. And then 2014, we see a massive scale of probably a sediment wave going down. This can be viewed perhaps better here in that image, even though it's difficult to distinguish, because you see that the river on May 14th is loaded with sediments, but it also appears that Trishuli was also more or less, at least buried partly, on the sediments that came down following the earthquake. So what actually caused then the high losses? It's the economy, stupid. That's what Bill Gates said. I would say in that context, it's the geomorphology. Okay. So what I want to do in the next part is to show how we actually can use this idea and to test the idea that geomorphology and earth surface processes are responsible for the major damage, and how we then actually can use this information to predict damages, and as such also to support planning and at a regional scale to devise locations where hydropower projects should be created or set up, and where not. So in that context, I'd like to talk about landscape sensitivity. So we need to look at a broader spatial scale and temporal scale, and not focus so much on the hydropower site itself. Rather, it would be interesting to look at landscapes and actually how resistant and how sensitive they react to perturbations. So perturbations in that sense could be major earthquakes or strong rainfall events. So sensitive landscapes are close to thresholds of mass wasting processes. So once you perturb the landscape, hill slopes will tend to trigger landslides and move a lot of sediment towards the rivers. So these landscapes react quickly to external shocks. However, landscape sensitivity is just not a landscape property. It often reflects some inheritance from past environments. It's often associated with weak bedrock. I want to show more that, well, it's actually a property of perhaps transient landscapes or those landscapes that experience very rapid uplift rates. Okay, so just to showcase what that actually means, a transient landscape. So what is a transient landscape? It's a landscape that adjusts to new boundary conditions. It might be a landscape that adjusts to climate change, a landscape that adjusts to drops in base level, so it drops in erosional base, let's say, due to sea level changes, for example. So what we see here is a landscape is not in the Himalayas, it's in the US. It's the Little Grand Canyon in the Yellowstone Park, which basically cuts through volcanic rocks that were emplaced a few 100,000 million years ago. And so the interesting thing is that as a reaction to that process of basalt flows, the river then had to re-incise back to form a new bed. And well, that occurs here along a significant nick point that slowly migrates upstream. And well, the interesting thing that one can see from here then, if we zoom out a little, is, and that's a satellite imagery of the same region, is that, well, the hill slopes close to, or that are adjacent to the river, and yes, up here, that's where the waterfall is, that's migrating upstream, that if we just use vegetation density as a proxy for hill slope activity, that there seems to be some kind of lag time between, well, where the nick point currently is and how long it actually takes for hill slopes to react. That is something that we might look at into more detail now or in the future also. It is something that others also looked at. For example, Hurst et al. Showed that, well, hilltops create or react, of course, often in a bit delayed way to upstream migrating nick points. And that's a process that's happening actually on scales of thousands, 10,000s of years. Of course, that's not just a linear feedback between rivers incising and hill slopes reacting. It can be a complex feedback, and in a study by Antonio Scully and his co-authors, he showed actually that this can invoke quite complex feedbacks. That's a small-scale example that they investigated, but in fact, it starts with an initial position, and you have that little nick point. It migrates upstream. Upstream migration will debuttress the adjacent hill slope, which will react in a delayed way with landsliding. It will create a new step and then stabilization, and then that's basically back to the initial position. And so we might create these complex feedback mechanisms between river incision on the one hand and hill slope response on the other. So in the end, what happens by this hill slope channel connectivity or coupling is that a lot of coarse material will be delivered to the stream network, and that has been shown before, or is currently investigated by a project by Georgie Bennett, for example, Boulder project, which is happening in Nepal, as far as I know. But it has also been shown in this nice study by Kristen Cook in Science, which impressively shows how basically channel and hill slopes are connected, and which is very important for, well, all the delivery of material towards the river. Okay, so how can we then express that in a kind of modeling framework? So what I'd like to use and employ for getting back to predictions of hydropower damages is going to adopt techniques that we actually use in tectonic geomorphology. Okay, so because here we actually investigate how transient landscapes form, and we look at ways how to characterize them. And what we basically rely on is relatively simple models of that represent the hydrology of river and incision into rivers, and relatively simple models also of hill slope development. And so in this slide here, I'm just showing how such a model could look like. Now what you see here is a river network that evolves, or a landscape that evolves as a response to long upscale or long updrift, uplift, sorry. And this model is also equipped with different lithologies, and you see how as soon as the river cuts through different lithologies, that creates waves of transient landscapes that experience a renewal, okay? And as such, also the slopes react on it with over-steepening and denudation. So what's happening in these landscapes is actually quite easy then. We can display that with river profile analysis. So you can look, so the plot here basically shows distance upstream from a river that, well, basically starts at elevation of 0 and then goes upstream. And here on the y-axis is the elevation, and well, what's happening there is then if we insert a rapid base level drop, is that basically the wave of midpoint is actually traveling upstream and renewing the landscape then. So in order to analyze these data, and or even these models are driven actually by a quite simple model. It's the stream power incision model, which is expressed as that the change at any point in the landscape along the rivers is a function of uplift on the one hand side, and on the other hand incision. And incision is modeled by the stream power model, which is shown here, which is basically a simple function between well, stress and strength. So the stress is exerted on the river bed by discharge, which is an upslope area as a proxy here for that, and slope, and that's modified in how by strength of the bedrock, which is basically encapsulated in that parameter K. So which is a measure of the erosion efficiency. Now, if we think that, well, everything is, let's say, in steady state, then dz over dt just remains 0, and we can solve that or reorder that equation and solve for S for the slope of the river, which then is a function of upstream area, uplift, and bedrock erodibility. To this end, we can basically define what we would expect, what kind of slope we would expect at any site in the river network if we have steady state conditions. And we can also compare that what we actually have. And well, that's what so-called KSN does. KSN compares the actual slope of a river divided by what we would expect of slope. And So we normalize by the expected slope at a particular upstream area. There's also a different way to do that, which has been done by, or introduced also by Rahul Debani, who I've seen also here as being participating. So it's called MCHI. We just have a different coordinate axis chi here, and the thing is the same. I'm using here MCHI, but basically that's exactly the same as KSN. So again, if we visualize that well, we see that upstream migrating over steepened river sections, which are indicated here with this light or with this yellow color. Okay, now let's take a closer look at the Roorkee earthquake again. And what we want to aim now is to derive a model that helps us explain the occurrence of losses. So traditionally, ground shaking directly impacts hydropower facilities, as it can lead to ground settlement and structural damage. Beyond some critical value of ground shaking, we can assume that the damage is related to ground shaking. We can add some geomorphic activity, which may be instigated by ground shaking, thus accounting for the impact of landslides, rockfalls, and so forth. But unless there are some nonlinear relations between the two, we can still assume a similar relation as before. However, if we add landscape sensitivity, by however means we quantify that, we could come up with let's say, a bit more complex model, which would reflect high damage if we had high ground shaking and high landscape sensitivity. But if our landscapes are not particularly sensitive, well, then even high amounts of ground shaking do not lead to big damages. In turn, however, if even minor degrees of ground shaking would basically incur high losses if our landscapes that we are dealing with are highly sensitive. Okay, so that's the idea. Let's now populate this model with data. Now for ground shaking, we take peak ground acceleration. Peak ground acceleration is actually quite, or measures how hard the earth shakes at a given point, and is approximately related to building demand and design. So I acknowledge here, and we will talk about that later perhaps also, that of course these measurements and models are particularly difficult to make, and spatial predictions might be might be uncertain too. What I took here is data from the Roorkee earthquake main and aftershock, and combined them both with maximum operator, so to get one value of peak ground acceleration at each point. So we compiled a number of hydropower project damage records based on gray literature, mainly newspaper articles, websites, and so forth, and we classified those into an ordinal scale, either no damage, 0, 1 for low. Low is then mean slightly damaged, but still in operation. Moderate site is damaged, but the plant is not in operation, but can soon be fixed. And severe damage is then either totally destroyed or non-operable for years. Okay. Then, in order to see, well, what's the geomorphic activity that resulted from ground shaking, we looked at landslides that were mapped by people from Durham, I think, published data at Hume Data, so that's an open access data. And well, then landscape sensitivity, well, here's just the idea how to use that MCHI or KSN, assuming that, well, the transient response or high uplift rates are indicators for landscape sensitivity to extreme events. Okay. So let's look at some of the results. What we can see when looking at the spatial density of landslides is that our model holds quite well. So here on the x-axis we have peak ground acceleration, and on the y-axis mchi. And if we measure landslide density just happening as it's happening in the vicinity to the river network, that we can see that that triangular shape that we hypothesized before. So is that now also reflected in the way that we see damages to hydropower? Well, we try to assess that with a multinomial logistic regression. So it's a multinomial classification approach. And well, this approach basically highlights that we see again this pattern that, so these are no regression lines, but lines of decision. So everything which is beyond that line, there would be expected severe damage. What is below that line, we would expect no severe damage, but either moderate, low, or none, and so on. And that's also true for the other one, moderate beyond that line and low and none on the other. And what we can see from here, well, we get those patterns that we would expect, but there's in general a low separability of classes. So perhaps our classification in none, low, moderate, and severe is too detailed, in fact, to be worked out by that model. So we reclassified into binary classes. The one is none and low, and the other one moderate and severe. And we tried to do that again with the Bayesian multivariate logistic regression. And these are the results. And the good thing about this Bayesian regression is that it also better, accounts for, well, the idea that we basically have a limited amount of data, and well, that's the model that we can actually credibly retrieve from that data. So what we can see here is that our decision boundary also has this characteristic shape, which reflects basically that beyond that, we need to expect moderate to severe damages at a probability. That probability is basically here at a value of 0.5, and what is below, we have a low probability. And what our model also suggests is, well, that both predictors, peak ground acceleration and mchi, are credibly important in a way. And well, that classification basically works quite well, is shown by the area under the curve metric, which is a metric to assess the performance of a classifier, and which has a maximum value of 1, and in our case it's 0.91 to 0.94, given our data, and well, points at that this model basically works, and we are actually able to predict the degree of damage that any hydropower project would experience. Okay, so we can actually use that model and apply it to larger scales if we like. I mean, we know it's critical because the geological situations vary all over the Himalayan arc, but nevertheless, we simply applied it again. And well, what we combined then actually is that we took peak ground acceleration, what we estimate to happen within 10% probability in 50 years. That's published as the so-called GSHAP, the Global Seismic Hazard Assessment Program data. So we have for each circle that is shown here, which depicts also a bit the spatial resolution of that data, the expected peak ground acceleration at a probability of 10% in 50 years. And well, what we can also easily calculate is mchi. Mchi, the river steepness. Well, we have perfect digital elevation models. Well, not that perfect always, but we have them at a global level. And so we can easily calculate mchi for the entire Himalayan arc. And well, based on that and our model, we can easily then project the probability of moderate or severe damage and map these probabilities spatially. And you see that this is a combination, of course, as our model is, of peak ground acceleration and mchi. And what it shows in particular is, well, when we compare that to the current distribution of hydropower projects, we see that 25% of existing and currently constructed and planned hydropower projects are actually in a zone that will experience high damages if there are earthquakes to happen. And that's also true for more than 10% of the Himalayan drainage network. As you can see from the image, high, so it's the lowermost one, high projected hazards along the main occur along the main physiographic transition, and which highlights the regions with pronounced seismic activity as well. Now, of course, there are a lot of things to discuss and to criticize, I guess, in our approach. Of course, it's highly oversimplified. The model has only a few input parameters, but these are or have their uncertainties on their own. PGA in that case was based only on a few accelerometers, and landscape sensitivity, of course, is not just a measure of MCHI or KSN, but other geomechanical properties, lithology, regolith cover, past glaciations, and so forth. But I need to stress always that a more elaborate model is difficult to reconcile with the scarcity of data that we have. We only had 41 observations, and it's difficult to fit a very complex model to this amount of data. So what we can expect that there is ongoing landscape recovery from earthquake and more damage, perhaps, likely to come downstream once sediment waves go downstream. Such a sediment wave can nicely be seen here on the right-hand side, which shows massive sedimentation following the Wenchuan earthquake. So, and at the end, I'd like to stress also that a regional study, of course, cannot replace the detailed on-site investigations that are necessary, but it can be used to assess risks of tapping the remaining hydropower potential. Before I come to the end, I'd like to, at the end, look at a few research gaps and where I think our project could, step in and go a few new avenues. So one of the most research gaps, I think, is that, frequency distributions of sediment transport events are really hardly known in the Himalayas. They are difficult to measure. We know that. So in our studies so far, we particularly looked at these mega extreme events. So the picture that you see in the background is basically the accumulated effect of 2-3 earthquakes during medieval times, a massive amount of sedimentation that occurred in the Pokhara Valley, and that we have published about 4 years ago actually. Okay, but we need more data also for the smaller events, and so we might need to look at tapping new data resources, and one of these resources is definitely sedimentary data on the one hand. But on the other hand, sediment preservation is an issue in the Himalayas where sediments get eroded pretty quickly. So another thing we might look at is techniques such as environmental seismology. So these techniques are able to describe sediment transport events, as has been shown by Kristen Cook and her co-authors, for a glacial lake outburst floods in Nepal. In a study that I conducted with Jeremy Bricker, we also looked, for example, at data from social media. So we took videos that were published on YouTube of a flood that occurred when a landslide dam along the Kali Gandaki River broke, and we were actually able to retrieve a lot of information from these videos that were uploaded to social media platforms. Finally, I'd like to stress that we should also engage in discussions and in possible exchange with those people that are running the hydropower reservoirs and hydropower stations. They should actually have a lot of data from how much sedimentation happens within their reservoirs, and I think we should tap that resource. Another thing we should look more closely into is understanding cascading events and sediment pathways. So you probably know that picture. It shows Kedarnath, a pilgrim village in the state of Uttarakhand, and it goes up to the Himalayas, in the high Himalayas, and well, it was the site of a very destructive flood during the Indian floods in 2013. Now, the major destruction that happened here was probably due to a combination of processes and events, which included the outbreak or outburst of a relatively small glacial lake upstream, but also rain on snow cover, but also you see a lot of sediment involved here. So understanding these different sediment sources and pathways, I think, is extremely important to make predictions on what on the amount of sediment and geomorphic impact is to be expected downstream. However, these pathways are not only in space, but also in time. And I think one important thing we need to recognize is that there's also a path dependence of natural hazards. That means natural hazards are also contingent on what happened prior. And so we can see in the Alps, for example, that a lot of processes that are going on along steep walls and also downstream of high mountain areas are still the result of deglaciation after the last glacial maximum, or after some areas got ice-free after the Little Ice Age. So understanding how long-term landscape changes do affect and do prime the spatial distribution of natural hazards today is, I think, of utmost importance. And for that, I would, in the end, advocate for better linking or trying to link models of long-term landscape evolution to present-day hazards and risks. And well, with that, I'd like to finish my talk, and I thank you for listening. Thank you.